We're going to start talking about periodic trends. Okay, this is a series of periodic trends that we're going to have to get through. And the first one that we want to talk about is something called effective nuclear charge. Okay, sounds like something very nerdy, right? The effective nuclear charge. It's actually a simple concept. Let me put it this way. If I start with hydrogen, okay, I start with hydrogen, it's got one proton in it, and there's one electron, which is flying around on the outside. So what's the effective nuclear charge on that electron? Okay, and the answer is 1. The reason being is that at this point, one proton here is affecting that electron with a certain pull. So it feels like one proton is pulling on that electron. Okay, so this is hydrogen. If I go to lithium, lithium's nucleus is a little bit more complex because I've got neutrons thrown in there. And neutrons just add mass, not adding any charge, of course. But I've got 3 protons on the inside. Now, if I look at this, and I use a Bohr model for this. Okay, remember that it's a Bohr model, so this isn't exactly the way it's represented. I'm just using this to show you what's happening. So I've got 2 electrons in the very first orbit. Okay? So this is another way of writing this, that you may be familiar with right now, is that this is 1s2. Okay? So the first level has 2 electrons and it's full. That means I got to go to the next level. So I've got to expand my level somehow to get my next 1 electron for lithium on the inside. And in doing so, I now have a 2s1. Now I've got 3 protons that are in the inside, but what's going to happen from that inner core, that core of 2 electrons, on this outer electron? Think about charges. You're right, it's going to repel. So this electron is repelled by a little bit. It's sort of protected from the positive charge that's on the inside. So I've got to look at this not just as nuclear charge, but I can look at this as an effective nuclear charge. And the effective nuclear charge for lithium has been measured to be 1.28. Okay, as far as positive charges go. So the outer shell electron only feels a pull of 1.28 electrons, or protons worth, from those 3 protons. That electron is being shielded by the other 2 electrons. And that's an important term. Okay? These 2 electrons here, the core electrons, shield outer electrons. And it should be noted that I have now introduced something that's a term that's actually very important. Outer shell electrons. Another way of stating outer shell is to call them valence. Okay? Valence electrons are the electrons in the outermost shell of any atom. They're the ones that do all the bonding. Valence electrons are crucial to all of chemistry. So valence electrons are only the ones that are on the outside. Okay? Now, if I look at beryllium, beryllium is 4p, okay, so it's got 4 protons in the center. If I look at the orbits that I've got here, this one still has 2 electrons, okay, that's the 1s shell. And now I go to the next shell, and it's got 2 electrons as well, that's the 2s. So here's 1s2, 2s2. The 2s2 is the valence electrons. Now here's a question that we've got to ask ourselves. When I start adding electrons to the valence, are they going to shield themselves from the proton charge? It's an interesting question. Think about that for a second. Go ahead and hit pause. And I want you to stare at the ceiling and ponder. And I want you to do this while you're doing it going, okay? Or if you have a beard or a mustache, start twirling and going, aha. You know, or my daughter, she does this. She takes her lip, and when she's really thinking, she pinches her lip, and she thinks like that. So I want you to do something very pensive right then. I want you to stare at the ceiling, and I want you to think about this for a second. I want you to come up with the idea. Does that other electron actually shield the other electron that's in the outer shell from the proton? And how would we be able to determine that? So go ahead and hit pause. Think about this. Okay, are you done thinking? Well, I hope not. But you're done thinking about that, right? So we look at these electrons, And if I add one more proton, if this other electron doesn't add any shielding, I should see this just go to 2.28, right? Because this other electron isn't affecting anything. It's just these core electrons. If this one does, I should see a value that's less than 2.28. As a matter of fact, I do, and what I end up seeing for effective nuclear charge is 1.91 effective charge units from the nucleus. Aha! So that means that outer shell electrons actually do some shielding, and as a result, what it does is it lowers the overall impact of the core protons on those valence electrons. If I jump up and I go even further, so let me go a little bit further. Let's go up to fluorine. Fluorine has 9 protons. Okay? And I've got those 2 electrons at the 1s, 2 electrons at the 2s, and now I've got 5 electrons at that point, all right? Now notice what's going to happen. As I've got 9 electrons there, what happens to the effective nuclear charge? The effective charge drops down to 5.10. Okay? That's a significant drop. That means those outer shell electrons are really being shielded by the core electrons from the nucleus. All right? And this is a trend that we end up seeing. And this is an important trend because it kind of drives all the other trends on the periodic table.